Hi, I'm Fahad Safraz, and I'll be presenting our work on semantic-aware representation learning for continual learning, where we leverage semantic relationships between objects and sparse representations to efficiently learn from an ongoing data stream, achieving a better stability-plasticity trade-off. Deep neural networks were originally designed for static batch learning, assuming that each batch is representative of the entire data distribution. However, this doesn't apply in continual learning where data arrives sequentially and the model only sees a small portion of the data from the current task. This creates a problem of catastrophic forgetting where the model forgets what it learned from earlier tasks as it adapts to new ones. The central challenge in continual learning is balancing stability and plasticity. Stability is required to preserve previous knowledge, while plasticity helps the model to adapt to new tasks. Existing approaches often prioritize one over the other, leading to either slow adaptation or forgetting of previous knowledge. The key challenge is to strike an optimal balance, enough plasticity to learn new tasks quickly, but also enough stability to retain what's already learned. As previously alluded, continual learning techniques often treat stability and plasticity as separate goals, failing to account for their complex interplay. Additionally, dense representations don't capture the semantic structure, leading to interference between the representations of the objects. The brain, however, organizes knowledge using semantic structures, forming associations between related concepts. It stores information in sparse codes, efficiently encoding semantic similarities and supporting learning and retention. We hypothesize that by leveraging semantic structures, a continual learning model can reuse and consolidate overlapping concepts, mimicking the brain's sparse coding and semantic associations to balance stability and plasticity. To this end, semantic aware representation learning (SAR) emulates sparse coding in the brain and employs a principled approach to capture the semantic relationships between objects and uses them to guide representation learning. SAR leverages activation sparsity to emulate sparse coding and represents each object through semantically rich object prototypes derived from the mean sparse activations of the object samples. These prototypes effectively capture the semantic structure of object relationships, allowing the model to reuse and consolidate knowledge efficiently. By capturing the inherent similarities between objects, SAR leverages semantic relationships to guide the alignment of new object prototypes with those of similar classes from previously learned tasks, while promoting separation from dissimilar ones. This alignment encourages a structured representation of knowledge, facilitating knowledge transfer across tasks and reducing interference. Furthermore, SAL incorporates prototype regularization to ensure model stability, mitigating the risk of forgetting previously learned information and fostering effective consolidation of knowledge in a cohesive manner. This mechanism enables the preservation of valuable representations while adapting to new tasks, ultimately enhancing the model's overall learning capabilities. In our experiment, SAL consistently outperformed other rehearsal based approaches across various continual learning settings. Notably, under a low buffer regime where the model has limited samples from previous tasks, SAL effectively retained knowledge and consolidated it as it learned new tasks. Notably, as dataset complexity increased, especially with high semantic similarity between classes, SAL showed even more pronounced performance gains. These results are impressive considering SAL achieved this with just a single model, unlike other state of the art methods like ICLR and SCOMR, which rely on multiple models. Additionally, when adapted to online continual learning settings, even though SAL is not specifically designed for it, it provides strong performance, further validating its versatility and efficiency. Furthermore, we show that SAL effectively retains and refines the semantic structure of object prototypes across tasks, consolidating new knowledge while preserving relationships between previously learned classes. The model's semantic coherence improves over time, with related classes showing higher similarity post training. Finally, we show that SAL enhances the stability plasticity trade off by improving stability without sacrificing plasticity, reducing recency bias and effectively preserving knowledge across tasks through semantic aware sparse learning. Thank you for your time. For more details, please refer to our full paper.